So that was a general introduction to parallel computing, and now we come to a different section here, which points out that society actually has addressed many of these issues already. And so it says that the fundamental principles between parallel or concurrent computer are actually sort of similar to those used in society. And you could even argue that society partly exists to perform the same type of synchronization and communication functions that are the backbone of parallel computing. And there's an sort of general idea. You can say, why the hell do we use parallel computing? Why don't we just build a single processor that runs very fast? Now, the trouble is that we already see in society, namely, although there are stories about Superman, we don't actually have Superman, at least not Superman. And so when you have a big problem that's too large for one person, you do not hire a Superman typically, but you just put together a team of conventional people. And so that's a key principle, that when you have a problem that's too big, you don't get a bigger computer in terms of the size of the chip. You get lots of ordinary computers and put them together to solve the problem. And we have here some examples which reveal my fact that I came from the United Kingdom originally. I discussed how you would build Hadrian's Wall, which was a wall built many years ago to separate roughly England and Scotland. All right, so here we are building a wall. And we want to build this wall as fast as possible because those people up the north there are getting pretty annoying, and so we want to get a wall between us and Scotland. And so we produce a parallel processor, which is a set of masons which lay that wall in parallel. And here I've drawn 8 masons, and they each, of course, have bricks. And each mason is responsible for part of the wall. This mason is responsible for this gray part here, this one for this red part here, and so on. So the way we do parallel computing for building a wall is actually to take the data, which in this case are the bricks of the wall, and we divide the problem into parts and put one part for each processor. We do assign a mason to because this is a local problem where one brick has to be next to a neighboring brick. It is convenient to make certain each mason has a geometrically compact region, just as we saw in the previous problems. So this is like those scientific problems. Another important issue here is what issues are there with having multiple masons? Well, we have an issue here. We see that these masons overlap. And so when they, in some sort of distance measured by the length of their arm, there is some overlap issues, and the masons have to coordinate. So that's the communication necessary. And the masons communicate with each other at the boundaries of the wall, and the sort of problem of how much that communication causes is measured by some ratio of the overlap region to the actual length of the wall. So we can try to see how fast we can build the wall. So it's something, by definition, it's the number of bricklayers times the efficiency, how well the bricklayer works in the parallel situation compared to the sequential situation. And on these general principles, this efficiency would be 1 if there was no overlap. And so it's something to do with it's some 1 minus a constant times the overlap distance, which was, remember, the length of their arm, times the length of the wall assigned to each mason. So if you measure these all in meters and say the overlap region is about 6 meters, then that's 6 over the length of the wall assigned to each mason. It's not the total length of the wall, it's the length assigned to each mason, which is the total length of the wall divided by the number of masons. So there was a law which said that it was hard to do parallel computing, and originally it was stated that we wouldn't be able to do parallel computing, but this problem here shows we can, and there's a key principle to do, and there was a reason why they got this conclusion was reached. They didn't actually note that the key issue was that you need to have big problems to be able to get parallelism. And there was also some problems, or at least some implementations of problems, which use existing software which are impossible to parallelize. The problems we're looking at, recommender systems, search, clustering, machine learning, those can all be parallelized efficiently. And so let's suppose we want the speed up to be greater than about 0.8 times the number of masons, so that's an efficiency of 80%. And in fact, we can see what the principle is. We put that constant, which we had in the previous slide, to 1. This is then the overlap over the length. So if the overlap is 6 and the length is actually 30, this is 6 over 30, which is 0.2. And so we get an efficiency of 80%. So, and if we have an overlap of actually an L of 60 meters, then the efficiency is at least 90%. So, this gives the important principle. You need, parallel computing will work as long as the amount of work assigned to each processor is big enough. And this corresponds to this number 60 meters. If I give that mason enough wall to build, the overhead of interacting with his colleague at the edges will not be important. On the other hand, if I give them a small amount of work to do, namely if I make the length of the wall about the same size as the overlap, which is actually how it was drawn, then we have the well-known principle called too many cooks spoil the broth. Namely, they all interfere with each other. So that's actually important. You can now apply this to cooking. If you want to cook fast, then if you have a big data cooking problem, namely the problem it takes a long time to cook is you just have to cook a lot of things, then you can solve that with lots of cooks, because each cook can boil the soup independently. However, if you only have one meal and the customer wants that meal in 10 seconds and you haven't cooked it, however many cooks you have, you will not be able to solve that problem, because it is not possible easily to speed up the cooking of an individual dish. What's easy to do is to speed up the cooking of 1,000,000 dishes. You just do it in parallel. So that's a really important parallel computing principle. You need large problems to get good parallelism, but only large problems need parallelism. Because if you have a small problem, you will be foolish to use parallelism. You'll just get an inefficient implementation. So that's a key principle. You must only use parallel computing when it's necessary. If you use it when it's unnecessary, you'll get bad answers.